Alright, we're gonna do a cool stream. So, we're trying to figure out how three-dimensional neural nets work. If they're on three, yeah, if you have three inputs. So I've I made some mat plot visualizations, and actually I think we did because I was talking to ChatGPT about it. It was like, you should do agglomerative clustering of the activations, and oh yeah, I forgot to you should do agglomerative clustering of the activations and the visualization, and yeah, and then you can kind of possibly, yeah. So I mean, like, we're trying to we're trying to intuit how a human would program, how you would set the weights and biases to yeah. So we're trying to compute okay. Yeah, okay, so this is like a good, so let me get the, yeah, like, this is all the visualizations, but the main one is this guy. So yeah, we're gonna try to figure out how this guy works. Okay, so like these are the inputs, right? So we have we're in 3 dimensions, and yeah, we're just doing binary inputs, because I don't really know why. It's just binary. Yeah. So anyway, these are all the inputs possible. There's like 8 of them. And then this is the target function, right? And so it's saying, like, this input I want to map to red, so on and so forth. So we can kind of, I think, give it the interpretation that these 3 inputs we are separating from the other inputs, and kind of in particular, because this function was randomly chosen, but it happens to be separating an input and its negation. And wait, let me see. Yeah, I'm trying to. I believe that you can't actually. I don't think you can actually compute this, like, with a single hyperplane. Yeah. I mean, if you just think about it geometrically, right? Because, like, this is a corner of a cube. This is a corner of a cube, like the opposite corner, one of the opposite corners. And so if you're putting both of the, like if you're putting opposite corners of a three-dimensional cube on one side of a hyperplane, like you have to be including other points. I don't know what those other points are, but like, I mean, we are including this point, but okay, so anyway. So, conjecturally, this function is not linearly separable. It might be, though, you know, like, linear separability is kind of hard to intuit. So, anywho, we're gonna work backwards, okay? Because that's better. So we can see, yeah, so I should explain the visualization, like, you know, I mean, should I explain it? You know, like each layer, these are the inputs to this layer, which are these inputs, but like the rows have been sorted according to the clustering of these activations, right? And then this is the target function. So that totally makes sense. Okay, so anyway, we're gonna go to, so like this is the output. It says single dimensional output. But we can see that the units prior to the single output are correctly computing the function. So it seems that the function is first being correctly computed at this layer, and so what that means is that the previous layers have mapped all of the activations onto these activations, and these activations are linearly separable, apparently. So I think like the first thing to note is the blue inputs have been mapped onto these 2 points, and the red inputs have been mapped onto like three points. It's kind of like this is, you know, yeah, kind of 3 points. Yeah, it's kind of like, I mean, it'd be easier if we can make all the activations ternary, but I don't know. I mean, you can't like train SG, you can't do gradient descent on ternary. Although I know they, you know, there's bitnet. I think the way bitnet work, because they map to ternary activations like +1, 0, -1, and I don't know how they do it though. I think they like train the model normally, and then they no, I have no idea how they do it. I have not read the paper. Anyway, so let's first talk about, you know, this layer 3 activation. Like, what, you know, this is where the target function is being correctly computed, right? Like all 3 activations here are correctly computing the target function. So how does it do it? You know, how do we set the weights and the bias to, you know, effectively we have 2 points on the 3-dimensional cube, and like 2 to 3 points on the three-dimensional cube, and we're just trying to put a hyperplane in between them. You know, which is a simpler task than like at the input, where you have I think it was 3 blue points and then 5 blue points, or yeah, 3 blue points, 5 red points. So we've reduced the number of points, which makes the problem easier. Anyway, yeah, what's... yeah. Right, like, right, so like I'm trying to intuit the weight vector that would perform this separation. And I mean, there's kind of 2 observations. One is, if you take this column and you negate it, then you're 1 away. Like, it's correct except for this top row. So you could set the weight vector to you know, like, put the highest magnitude on this column. Like, yeah, but then set the other weights so that when the other weights are red-blue, it overrides the largest magnitude guy. Yeah, I'll go with that. We'll say that's probably what it's doing. So if we look at the layer 3 weights, which we're going to do, I predict that, I mean, also all 3 neurons, all 3 columns are computing the exact same function. So I predict what those weights will look like. This will be you'll have a blue, which is -1, in the first column. The highest magnitude will be negative, might not be -1, but like it'll be negative in the first column. And then the other 2 columns will be red-blue. Yeah, they'll be red-blue because they're going to overrule the largest magnitude weight, but only on this row. So like on every other row, they'll cancel out. I'm not entirely sure what they'll do on this row, because this row needs to be, yeah, what will happen on this row? If it's red-blue, it'll be very negative. And it will override this guy by definition. So maybe that's where the bias comes in. Yeah. Dang, man. I mean, another... Yeah, I'm just gonna say the bias saves that. Okay, so let's just look at the actual weights. It's blue. I did say that. I said the first column. I said the first column's gonna be blue. And then blue-red. Is that what I said? Oh, it's different. Blue-red. Oh, oh, blue-red, yeah. Blue-red makes a negative. Oh, yeah. Okay, so anyway, that that worked, right? Like, that's a mechanistic interpretation of this layer, right? I mean, almost to the point where I, as a human, you know, or I could be an AI. You don't. There's no way of knowing. But I, you know, I almost figured that out. I mean, really, what you're doing at every layer, or is like you're solving like linear programming, or you have a system of linear inequalities, and but that's only at like when you're going directly to the target function. Yeah. So, okay. So let's try to interpret layer 2. Let's try to interpret layer 2 because what we learned from layer 3 is that this column is a big deal. It's basically doing error correction on this column. And it's doing the error correction by, you know, matching blue-red on these two columns. And so, like, you know, and so that error correction cancels out on these two rows. It cancels out on these two rows. It reinforces the, like, it's correct on this row. And, I guess it kind of goes to 0 here, and it cancels out here. So, so it's like we have to set up each of those columns in this layer to do that. Okay, so it's like these activations and these activations are the same. That's the way I did the visualization, right? It's just that they're sorted according to the clustering here in this visualization, and they're sorted according to their own clustering in this visualization. And these are the raw inputs. So, this don't actually, I mean, that doesn't look too bad. So, like, the first column is just separating these 2 points, which are neighbors because they differ by 1 dimension. Right, so that first column is separating like an edge in a 3-dimensional cube. The second column I see. Wait. No, I don't see. It's not entirely clear. Like, I mean, the second column is just like, I mean, basically it's just separating this 1 point. Maybe these 2 points from everything else. I don't think it has to do that, though. I mean, it could just be constant. No, it can't be constant because it has to mark. Well, yeah, no. it could be constantly red, I believe. It could just be constantly, it could be all ones. Like, if it were just all ones, this would still work. Yeah, it would still work. So, yeah, so I don't know why it's like, I don't know why it's inserting that blue. Doesn't need to do that as far as I can tell. And then the third column is doing something. It's still don't. Yeah, the third column is yeah, just separating this one input. It's kind of like tagging. I guess, yeah, it's because if it were red, then there'd be no way of distinguishing this blue row from all of the red rows. So it's basically just tagging. It's the one column separating this one input, this one blue input, from all of the red inputs. Yeah. Okay, so like the weights for all of this are probably not too hard. I mean, the first column is the weights are going to be identical to one of these, and then it's going to have like a relatively high bias because it's separating out everything else. So let's look at those weights. So they're blue, red, blue. Okay, so there you go. So the first layer weights are on this guy, and then they're it's like a high, I don't know, relatively high bias. Actually, it's kind of making that a 0. Okay, so it's actually just looking for red, blue. That's cool. Yeah, so I guess kind of like the blue rows are kind of being encoded in the first layer weight matrix, because this row is saying like, are you red, blue in your second in those dimensions? Like, if you are, I'm going to separate you from everything else. And then the last column is saying red, blue. Red, blue. What is the last column doing? I mean, like, the last column is specifically tagging red, blue, red. Except I think it's in negation. So it would have been better if this had said red, blue, red, but I think that's what it's doing. So like of the blue rows, 2 of them are encoded in the first row. One of them is encoded in the last row of the first layer weights. And as far as I can tell, the middle column, or the middle row, is not doing anything. Well, it just has to be all reds. Right. So almost as a human, you could almost understand that, or like you could almost program that, right? Like, this is your like input. You know, you're like, these are your 3-dimensional inputs. This is your target function. You know, program a neural net to compute that. And you're like, all right, So I'm gonna look for this red, blue feature. And I'm gonna put that in the first column. And I'm going to ignore the second column. That doesn't do anything. And then I'm gonna look entirely for this one input, red, blue, red. So like we're effectively like partitioning the blue rows into two conditions. And then once I have them like this, you can then directly compute the function, right? So like because like these rows are these rows, just different sorted. And, or I guess like in other words, you can separate these three from all of these. And we can separate those by that observation that, like the first column is correct, except for on this one row. And so the way to array is going to be like the negation of this column, and with an error correction on the other two columns to flip it blue. Because I mean, if you just directly negate this, you get like red, blue, blue, red, 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 red. And then you're like, yeah, but I want this, when this is red, blue, I want that to be very negative to override this value. And yeah, and that works. And also this middle column could just be all red. Like it's unnecessarily complicated. Okay, yeah, so, I mean, it's like, would you actually memorize that? Maybe. Okay, let's see, do we have any questions? No, I think, I can't even tell if this is running. I guess it's running, yeah, okay. Okay, no comments, that's fine. I'm going to do one more. We're gonna keep it three-dimensional, because, yeah, I've tried four dimensionals, and, they get pretty hairy. Okay, so we're gonna do one more three-dimensional. Oh no, this one is garbage. It just separates a single input point. So that's garbage. Cancel. Like this cancel thing used to scroll, but now it doesn't. So yeah. Okay, we need a different function. Okay, what do we have here? 1, 2. Okay, this is separating 4 from 4, so that might be fun. We'll see what happens here. Yeah, I had like these pairwise distance thingies, but they turn out to not actually be all that useful. So, okay, so like this is the function we're trying to implement, where we're splitting the thing in half. It doesn't look like you can do that with a single hyperplane, at least gradient descent chose not to in the first layer. It doesn't necessarily mean you can't, but yeah, and okay, yeah, so we're gonna try to do this one quickly. No, yeah.